In 2017, I sat across from 3 people whose stories rewrote everything I knew about survival. One had been told he had just 8 months to live. Another was fighting stage 3 breast cancer while her family faced war back home. A third endured the trauma of a double mastectomy and came out the other side with grace and strength. I wrote then, there is a life after diagnosis, and I believed it because they lived it. But 3 years later, cancer stopped being something I wrote about and became something I walked through alongside 2 of the people I love the most. Recently, another beloved one joined this journey. It's no longer a rare illness we whisper about. It is at our tables, in our hospitals, in our prayers. And yet, we still hesitate to say the word, cancer. But here's the truth. Science is moving. People are surviving. Battles are being won. And today, from right here in the Arab world, we speak to someone who's part of that movement, a researcher, not only helping treat cancer, but reshaping how treatment is being delivered. Because let's face it, treatment is hard, physically, emotionally, spiritually. It takes almost everything. But when science offers more precision, less pain, and better outcomes, healing becomes more than survival. It becomes transformational. Our guest today is Noor, a PhD researcher in materials science and engineering at the American University of Sharjah. Welcome to the show, Noor.
Hi, I'm glad to be here.
Thank you very much. Noor's work lives at the cutting edge of targeted drug delivery, rethinking how, where, and when medicine reaches the body. In one paper, she explored and researched how hydrogels, soft sponge-like materials, can deliver medicine. She also worked on another paper about liposomes. In another, she uses ultrasound to trigger drug release from microscopic carriers, delivering medicine only where it is needed and when it's needed. Her work is precise, promising, and fulfilled, with the potential to reshape how we fight this illness. Noor, you mentioned how science is becoming more personalized and precise. One example in your work is the use of liposomes, tiny carriers that deliver the medication through IV. Could you a little bit explain to us what are these liposomes and how the treatment is becoming more and more different?
Yeah, of course. So usually chemotherapy is delivered directly to the bloodstream. So you would just inject the chemicals, the treatment, into the patient's blood. But as we all know, that can have devastating side effects like the fatigue, the nausea, the vomiting, and the hair loss. And so what we try to do is that we want to overcome or to minimize these side effects. So instead of delivering the drug directly to the bloodstream, we encapsulate it. We put it into these like very, very, very small, like nanoscale spheres that are called liposomes. And they are made up of the same materials that make up our cells. So we say that they are biocompatible. They would not pose any harm to the rest of our body. And so what they do is that they would accumulate in the cancer areas rather than targeting the whole body and affecting healthy cells as well.
So liposomes, for listeners who don't fully capture what liposomes are, could we further dig deep into what do they mean, what do they stand for?
Okay, so liposomes themselves were discovered a while ago, but their use to deliver medication started in the 1990s, and there is actually an FDA-approved drug, chemotherapeutic drug that is liposomal based. It's called Doxil. And so to explain what liposomes are better, let's talk a little bit about the biology of cancer. So normal cells are very close to each other and they don't have a lot of gaps between them. But when you look at tumors or at cancerous areas, the cells tend to be further apart from each other. So you have these gaps. And liposomes are well within the perfect size range to fall into these gaps. So what we do is that we take the sphere that is made up of the same material as our cells, we put the drug inside of it, and then we let it flow through the bloodstream. Once it reaches regions where it can fall into these gaps, that's exactly what it happens. The liposomes kind of drop into the gap and they get stuck there. And so with time, the liposome itself can open up and it can release whatever drug it contains inside, or we can use an external trigger, something on the outside that can help it open up or like burst open in a sense and release the drug in that specific area. So it just makes the delivery a lot more specific in terms of cancer therapy. So that's how they tend to improve the chemotherapy treatment.
So are these the two factors that make liposomes a game changer compared to the traditional current medication cancer patients are going through?
Yes, that's what all nanocarriers offer, is that you first increase the specificity and you also increase the, let's say, the concentration of the dose that you are delivering, but to that specific region. So instead of having chemotherapy just systemically delivered to the whole body, you just concentrate the amount in that area that you want to target. So you don't have any, let's say, drug that is just roaming around the body.
Yes. And I think the treatment, cancer itself is definitely frightening, but the treatment that the patient goes through is even more frightening because it usually attacks the whole body, it causes hair loss, it causes a lot of psychological, physiological. So when we approach such kind of a treatment, it's actually a breakthrough in history.
Yeah, of course, definitely. Yes, it just the idea of people not having to suffer through the side effects, I think, is a game changer.
Absolutely.
Because it just gives them hope. It gives them the support, let's say the motivation to go through with the treatment. So yeah, it's definitely amazing.
When it comes to such a great innovation in the field of science and the significant impact it's going to have on hundreds of thousands of lives, could you describe this moment in science and this shift in how we approach healing?
I mean, it's, I think, something that every scientist and researcher dreams of, to see the product that they make, let's say their baby, affecting people's lives and having a great impact and just making life better in general. I think that's the most important thing, and that's why scientists and researchers, we start doing what we do, because we want to make the world a better place, just like one idea at a time. So if we reach a day and hopefully like we can cure cancer, that would be perfect. That's the dream.
Definitely, absolutely. One paper you and your colleagues focused on is the use of hydrogels. What are they exactly? And what makes them so well suited for this job, which is destroying the cancer cells?
Okay, so hydrogels are a different kind of carrier. So we say we can divide carriers to different types based on the material that we make them from. So liposomes, for instance, fall under lipidic because we use lipids to make them. But hydrogels are polymeric, so we're using a polymer. So this is like, think of a net, a web, and you have all of these like small parts to it. It just creates a big network where you can put whatever drug you like inside of it. And sometimes these, the way that they work is that these, the net itself, it can swell, so that you can have things inside of it. It can swell, it can also collapse on itself or open up, let's say, and release its targets. And what makes hydrogels so interesting is that they have a really high loading capacity. You can put a lot of your medication in them. And they are really good in things like transdermal delivery, or delivering medication across the skin. Because the skin is a very strong barrier. It's not easy for things to go through the skin. That's why it's so amazing. It protects our body from everything. So if you use something like a hydrogel, it can improve how the drug goes through the skin, and it can also make sure that, again, because all of these carriers, their job is to be more specific. So if you're using a hydrogel, instead of having to put, like, let's say the cream or whatever it is all over your skin, it will deliver to that specific region that you are targeting. So that's one of the things that make them so amazing.
So we use creams in order for the hydrogels to be applied on the skin? Or is there a kind of insulin patches or wound dressings?
So they can be in different things. There's some really interesting research about using hydrogels in patches and in dressings, and they can also be in products. Like some of the beauty products that we use today, they have liposomes in them, and they have micelles, and they have hydrogels. Yes. So cosmetics are always at, the head of the game when it comes to the new stuff. So they are being currently used, but in a different way. But it's a similar concept. You're trying to deliver a specific material using this carrier in a more specific way, like to target a specific location, and also to control the dose and the timing that it is delivered, so that not the whole drug rushes in all at once, but it can take a few hours for it to go in.
Has this already been applied, or it is still in the testing stage?
In terms of hydrogels?
Hydrogel, liposomes.
As I said, so Doxil is a FDA-approved drug. It's in the markets.
Explain to us, what is Doxil?
So doxorubicin is one of the chemotherapeutic medications that are currently used.
Yes.
And Doxil is basically doxorubicin in liposomal form. So this was discovered or started to be used, or was FDA approved in 1996. Yeah, so it's been a while. There are some other variations of it, and this field is very fast. So researchers are working, let's say, 24/7 to make something new. So if there is a hydrogel-based formulation or a liposome-based formulation that is much, much more recent, then probably there is something out there.
So what is next when it comes to these two specific breakthroughs in science? What is the dream?
Okay, so there is always, let's say, some technical aspects that we need to improve. So how the body gets rid of the nanocarrier after it is released, making sure that it really does deliver to that specific region, that there are, let's say, no strays going around and releasing elsewhere. And one of the main, let's say, problems is cost and large-scale production, because you're talking about something that really needs very specific conditions. It needs to be stable. It has a very short or specific shelf life. So these are all constraints, but that's part of the beauty of it, like trying to overcome these challenges and thinking of new ways to just work through it.
It's magnificent.
Yes.
And thank you for sharing this information and repeating some of them to our listeners.
Of course, yes. The objective is to teach everyone about what we do.
Absolutely. So we've explored how medication can be delivered through liposomes and the other examples we've mentioned. But what if we want to go deeper to reach a specific tumor or an organ? What do we do then?
Okay, so one of the approaches, and this is part of the work that we used to do, is to decorate the surface of the nanocarrier with a molecule. It could be a protein, a vitamin, a carbohydrate. You just put something on it that is present a lot on the cancer cell. So it's kind of like a lock and key. The cancer cells, they have a lot of these locks on their surface, and you would put the suitable key on your liposome or on your nanocarrier so that it will only go to that area. It will only fit in that area. And so that is called targeting or functionalization. Another way to make it better is to use triggers. So you either play around with the chemistry of the nanocarrier and you make it open up in response to heat, to pH, or maybe you can use something on the outside like an ultrasound trigger, or maybe lasers or something like that.
Could we control, for instance, when and where?
That's the beauty of ultrasound, and because it allows you to control exactly where and when you want to open it up. Yeah.
So that brings us to the second paper. Yes. A study that honestly feels like a science fiction. Tell us about the other side of your research using ultrasound to release drugs from micelles and liposomes. What are these nanocarriers and how do they work?
Okay, so with my cells, we're talking about a single layer, as I said, and with liposomes, think of a double layer. So the liposome is much more similar to the way our cells are structured in that sense, because it's a double layer of phospholipids, of the material that makes up our cells. And in the study that you're referring to, this is the work that I was heavily involved in Dr. Ghalib Husseini's lab at AUS, is that we load the drug, doxorubicin in our case, and then once it reaches its target zone, we apply ultrasound to it so that we help the liposomes open up. And it gives us more control over when we want them to open up or the region we want them to open up.
So the 2 points you've mentioned are one of the advantages of this targeted approach. What are the other advantages? Because compared to chemotherapy, I think there's a huge leap between the chemotherapy and such kind of medications or treatments.
The main thing about it is the reducing the side effects. It's also about achieving the right concentration that we want in the region that we are trying to target, and it's also about,
let's for instance say why it reduces the side effects. Is it because we're eliminating 100% chemotherapy?
No, we're not eliminating chemotherapy. We're putting chemotherapy in something that would deliver it to a specific location. So what chemotherapy does is that whatever cell divides quickly, it will attack it. And that's usually why people suffer from nausea, vomiting, and hair loss, because the cells in the stomach, the cells in your hair, they divide very, very quickly. So chemotherapy thinks that they are cancer cells. It doesn't differentiate between them, so it attacks them. But by putting them in a liposome, you kind of, let's say, prevent them from attacking these regions, the healthy cells that we don't want them to attack. So it's all really about specificity and more control, if we can really say that.
So you've studied biology, your study concentrates on biology. Am I accurate?
It's an interdisciplinary research. So you have biology plays a part, chemistry is a part because you have to create your formulation. The ultrasound brings in elements of engineering and also kind of putting the whole system together, let's say, is the engineering part as well. Yeah, so it's an interdisciplinary research.
So it's all interconnected together.
Yes, exactly.
Let's say when it comes to the real world challenges, when it comes to the treatment, such kind of a treatment, is it the safety? Is it the cost? Is it the accessibility?
It's a mix of all. When you're trying to do something like this, there's definitely more materials that you have to purchase. There's more time that you have to spend making it. So that tends to increase the cost. You also have to be a lot more careful in terms of storage and transportation. It's very delicate, let's say. So it needs very specific conditions for the drug to remain stable and to remain viable.
Which makes it more expensive,
exactly.
maybe.
Yes. So it's not just like a pack of pills that you can carry with you. You have to.
Even pack of pills are quite expensive.
Exactly. Yes. Yeah, that's pharmaceuticals. So that adds to the cost. Safety-wise, so liposomes, because they're made from the same materials as our cells, they're biocompatible, they're biodegradable, so they can break up in our body, and the body has its unique way of kind of filtering or getting rid of them. But there are always risks, let's say, because this is a very, very small particle. So there are some issues with accumulation in the liver or in the spleen or in the kidneys that can be problematic. But there's always work towards enhancing the formulation to avoid that, so that it just gets cleared out of the body and we don't really have to worry about that.
And now, after such kind of research with you and your colleagues going through different types of medications to treat an illness that many people are suffering from, the illness itself and the outcomes of the medication and the treatment, do you envision a future where patients might wear ultrasound-triggered implants or smart patches personalized, programmed, precise, in order to detect or help with the treatment?
I mean, yes, it's kind of here, but we still have a good way to go. So there are pills nowadays that would only, let's say, break down. The capsule would break down when the body needs it. So that, in a way, is like, let's say, the beginning of that dream happening. But yeah, to one day reach a point where every little illness or disease can be solved by a wearable patch or a bandage or a pill, that would be ideal. That would be perfect. Yeah, that's the dream.
It could happen.
Yeah. Yes, why not?
Because if we go back 10 years ago, so many things shifted.
Yes.
It's like we live in the future.
Exactly, yes.
We see robots on Dubai streets now.
Yeah.
So we never know what might happen next.
I don't think anyone who would have started in this field, like in this, let's say in the 90s or something like that, would have imagined what is happening today. So definitely, yeah, we're on the right path.
Actually, I can't thank you enough for taking us behind the scenes of a world that is often hard to imagine, but vital to our future. We began this episode with survivors, people who fought and won. But science is part of that story too, the invisible hands designing the next chapter of how we feel. When we think about someone receiving a medication that you researched, helped develop, someone in pain, someone healing, what goes through your mind as a scientist?
This is it, we've made it. Because this is the objective, is to make people's lives better. That's the ultimate goal. Even if it's just pointing a researcher towards like finding the cure. Like we are the stepping stone towards someone else even finding it. It's what we dream of, to help people. So yeah, it feels amazing.
You as a researcher, as an academic, what are some of the struggles that, let's say, you go through on a daily basis or even in your life? Is there a certain stereotype that you wish could change about researchers?
I mean, let's say the lab work is always quite frustrating. Mm-hmm. Not because it's hard, but because you hit a lot of roadblocks, let's say.
Yes.
So you write down your experiment and you have your steps and you think everything is going to flow perfectly, but it rarely does. Even if it does, you start questioning it. But yeah, it can be quite frustrating once you start, but once you get the hang of it, it's very nice to work in the lab. The stereotype, I think people watch a lot of films and they think it's like these people just sitting in the lab under the microscope and everything comes to us so magically. Yeah. Sometimes, yes, we do have a pleasant coincidence or something like that, but it's a lot of hard work. It's a lot of hours spent in the lab. It's kind of, let's say, lonely work, because most of the time you are working individually or you're working within a small group of people. And it's very repetitive. You have to keep repeating things. And so, yeah, that tends to be a little, not frustrating, but it can sometimes get on your nerves.
Anyone, actually.
Naturally, yeah.
What got you to this path? It's not easy to become a researcher looking into new ways to treat an illness that has frightened people for, I don't know, how many years?
Yeah, since a very long time.
Yes,
yeah,
such a very long time. So what got you here and how?
It was chance that turned into passion. Let's put it that way.
I love it, actually.
Yeah.
I think the best coincidence happen in life this way.
Yeah. I started doing my final project in my bachelor's with Dr. Ghalib's group. And after that, I kind of fell in love with the research, with the work that he was doing. I saw how important it is for the world, for people to be working on this. And I just kept going on and moving forward with it. And yeah, I became really passionate about the thing that we are doing. And that's kind of how it happened.
What was the research about?
So the research is the same concept. It's using nanocarriers, specifically liposomes, to deliver drugs to cancer. There have been, let's say, different drugs that were experimented with, different molecules, as I said, that were used on the liposomes themselves to improve the specificity of the drug. different triggers.
Yeah.
So they have, I think there was some work with ultrasound. There was also some work with near infrared light, some other triggers, some pH work, I think as well. So yeah, it's mainly focused around nanocarrier-based drug delivery.
All right.
Yeah.
In your research, has AI played any part?
Machine learning is a nice way for us to model release. So we can use machine learning to kind of help us predict how the drug will get released from the nanocarrier, the pattern that it will follow. And that in a way will help us perfect our formulation. So if we are aiming, let's say, for a specific way to release the drug, like instead of having it burst, we want it to just come out slowly over a period of time, you can use machine learning to help you with that. And it is being done. There is some research that is being done on that.
That's really quite interesting. Tell me about the life of a scientist like Noor. What do you do exactly? How do you keep up to date with the data that it is being, let's say, released on a daily basis?
You have to read a lot. It's as I would say, a researcher's work is never done. You never stop because there's always something to do. If you're running it's not just running your experiments. You have to read about what other people are doing. You have to analyze what other people are doing so that you can learn from them and you can fix what you are doing or introduce something new. You also have to constantly, let's say, network as well. You know, you read an interesting study that's being done in another country. Maybe you can get in touch with the researchers and just learn from their experience. You go to conferences to meet people. So that's a big part of being a researcher, just meeting people and just trying to learn from each other. Yeah.
So the cycle of research and continuous developing is a never-ending, let's say, a never-ending experience for you and for many in any field. Is there, let's say, a competition in the scientist field?
Definitely. But because everyone, well, there is, a lot of awards, and to keep your lab running, you do need funding. So competitions play a part in that because we need funding. Okay, but
explain to us, why do you need the funding?
Okay, so we are very blessed in the UAE that our research is heavily funded. So you have all of these, let's say, foundations and even universities themselves, they invest a lot into research. But in a couple of years back, this was not the case. Let's say you needed to go and to advertise your product. You want to tell people about your product so that people would invest in your product so that you can afford to buy the medication, afford to buy the equipment that you need. Maybe you need to hire some researchers into your lab. So you do need funding for all of that process. And that can be a big part of the competition.
Yes.
Because you're trying to prove to everyone that we have potential and we need you to support us to help us grow and achieve that potential. There is also trying, because research in the Arab world is kind of, let's say, new in a sense. So there is a sense of competition in that we are trying to prove ourselves, especially to the West, that we are just as capable and that we are just as brilliant. That is, part of the competition as well. So yeah, and people also like to be the best.
Absolutely.
It's human nature.
But why do you think that research in the Arab world is a new concept?
It's not a new concept as in like completely new, but us breaking into the scene is, let's say, more recent, like us publishing more heavily and showing the world what we have to offer. Because I think if you think about the university model 10 years back, it was about going in, taking your courses and leaving. And I don't mean just 10 years back, I just mean like a long time ago. But now it's, you go in and you want, or the university is trying to prove that we have research labs, we are putting something out there other than just education. So that's what I mean it in the sense that it is new. Universities now are much more open about the research that they are doing. The work that we are doing has reached the point of animal studies.
That's excellent.
Yes, in vivo work. So that is a huge step. But in order to put a medication out there, it is a very lengthy process.
All right.
So it can take you years or decades just to perfect your formulation. And then it can take another couple of years for you to perfect it in animals. And then you have to enter clinical trials, so testing it on humans. So it can take a very long time for someone to produce a medication, to commercialize it.
Yeah. Actually, bringing that up is reminding me of the COVID vaccines.
Yes.
Which actually didn't take as much time to come up with the vaccines. Why do you think there is a difference between such kind of vaccines and other sort of medications?
I would say part of it is the urgency.
Yes.
We were
Absolutely.
desperate during COVID times, and I wouldn't say there was any, like, obviously scientists they did their best, and but that sense of urgency probably introduced more need to produce something faster.
True.
And you also had, going back to competition, you had all of the big players, trying their hand at the vaccine. You're talking about like Sanofi, Pfizer. We had, I think, Johnson & Johnson producing one. So
Absolutely.
when you're talking about these companies, it's not just a small lab that's doing research. You have so many researchers and so many brilliant minds working at once. And I mean, yes, we can beg the question, like, was it done to perfection? We will never know.
Yeah.
Like maybe if we had more time, it would have taken longer.
That's
Again,
true.
we will never know. Hopefully we'll never have to find that again.
Thank you, Noor, a lot for your work, your time, and your devotion. And to everyone listening, may we continue to support science, speak openly, and believe always in healing, one discovery at a time. Thank you so much.
Thank you for having me. It was a
Thank you.
pleasure. Thank you so much.
The pleasure is mine. I'm going to have you again.
Inshallah.
Thank you.